Today's lesson is a start of our unit on forces in fluids. So we're just going to do a little introduction. We're starting with fluids and pressure. A fluid is any material that can flow and takes the shape of its container. So are fluids solids, liquids, or gases? Well, let's look at each one individually. First of all, a solid. Can a solid flow? No. Can it take the shape of its container? No. Okay, so that's not it. Liquids. Can a liquid flow? Yes. Can it take the shape of its container? Yes. Okay, so a liquid is a fluid. Okay. How about a gas? Can a gas flow? Yes. Can it take the shape of its container? Yes. So gases and liquids are both types of fluids. All fluids exert pressure. Pressure is the amount of force exerted per unit area of a surface. We'll talk about how fluids exert pressure in a couple slides. Okay, but pressure is the amount of force per unit area of a surface. So the formula is pretty simple. Pressure equals force divided by area. Okay, so let's do a couple examples or a scenario I think will get you to understand this a little bit better. Let's say there's a dance coming up and the boy asks the girl to the dance. But the boy is kind of short and the girl is taller. So the girl wears flats. Okay, so they're dancing at the dance, having a great time. And while they're dancing, the girl steps on the guy's foot with her flat shoes. Does it hurt his foot? No, not really. Okay. We get to the next scenario. Let's say it's a shorter guy, or a taller guy, but a shorter girl. So she wears some stiletto high-heeled shoes. And they're dancing around having a good time. But then while they're dancing, she accidentally steps on his foot. Does it hurt? Yeah, it certainly does. Okay, now why, if she weighed less probably than the tall girl, why did it hurt so much more when she stepped on the guy's foot? Well, because of pressure. Okay, the smaller surface area of the heel here, okay, the more pressure. Okay, so same force probably approximately, but over a smaller area means greater pressure. We're going to do quite a few demos with this in class tomorrow, okay, showing you this relationship of force and area. So kind of same force and smaller area will be more pressure. Okay, so we'll do some more examples with that tomorrow. The unit of pressure in the international system is a Pascal, and there is Pascal up there, named after him. Capital PA would be your abbreviation. A Pascal is the force of 1 Newton exerted over an area of 1 square meter. Okay, so a Pascal is a Newton per meter squared. Do a couple examples. What is the pressure exerted by a 3,000 Newton crate that has an area of 2 meters squared? Okay, the formula you know, pressure equals force divided by area. Put in your numbers. So pressure equals 3,000 was the force, okay, divided by the area, which was 2. So you do the math, you get 1,500, which we should probably round to significant digits. That would round to 2,000. And what is the unit label? Well, we just saw, if you have a Newton over meter squared, it is a Pascal. Okay, so 2,000 pascals. Okay, it's a fairly simple example. Let's change it around a little bit, and let's say, what is the weight of a rock that has an area of 10 meters squared and exerts a pressure of 250 pascals? So this time we are looking for weight. Okay. We're looking for weight. So P equals F over A. Okay. If we're looking for weight, which letter is that? Hopefully remember that weight is the force of gravity. Okay, so we're looking for the F in this case. The P we know says the pressure was 250 pascals. So 250 equals F. That's what we're looking for. Remember the weight, force of gravity, so F over A. The A was 10 meters squared. Okay. Now it's just an algebra problem. So if I change my color, go to red, multiply both sides by 10, so that we will, when we do that, we'll get the F by itself. Okay, the 10s will cancel. So then we have F equals 2,500. Okay, then we should probably round that with significant digits to 3,000. Now, what's my unit label? Okay, well, what is the force measured in? If we have pascals, the force is right there. The force is a Newton. Okay, so 3,000 newtons would be our answer for that. Pressure and fluid movement. Okay, fluids always flow from areas of high pressure to areas of low pressure. Okay. We're going to be saying this over and over and over again. Okay, you're going to get sick of me saying this. The fluids always go from high pressure areas to low pressure areas. It should make sense. Okay, think of turning on a fire hose. Okay, the water is high pressure, it squirts out to low pressure. Or let's say maybe you have a water balloon filled up and you squeeze that water balloon as hard as you can and it spurts out. It breaks and spurts out, going from where the high pressure was, you squeezing it, to a lower pressure outside. Okay, always goes from high pressure to low pressure. We are going to see lots of examples of this, not in this lesson, but in the next lesson. And in class, we're going to see many of them, and we're going to do a whole day on Bernoulli's principle. And you're going to be writing high to low, high to low, high to low repeatedly. Okay, last few things here. Pressure and bubbles. Fluids exert pressure evenly in all directions. Okay, I'm going to put a star by this. So fluids exert pressure evenly in all directions. So what shape is the goal? Okay, it's going to be a sphere. Okay, evenly in all directions would be, round in all three dimensions. Okay, it's going to be a sphere. Now I said we'd mention this earlier. How do fluids exert pressure? Okay, it's kind of an interesting word question maybe. But we know fluids exert pressure. Okay, we've been talking about that. You know it if you put, pour water into a cup or the air on you. Fluids exert pressure. How do they do it? Take a look at this picture here. Okay, fluids exert pressure because the molecules collide against the sides of the container or the object, whatever the case may be. Okay, so the molecules, okay, and then collide against the side of the container. So then we get to this question of pressure versus heat. Let's think about it. If, let's say, in this case, let's say we have a can. You have an aerosol can, an old can of hairspray, let's say. So you have your old aerosol can. Okay, there's my old aerosol can. Okay, and it's pretty much empty, and you're having a bonfire, so you throw this empty can in the bonfire. Okay. You have all these molecules in this can. When they get in the bonfire, these molecules are going to heat up, right? And they're going to start moving faster and faster and faster and faster. They're going to vibrate faster and faster and faster and faster and faster and faster. And they're going to start pushing on the sides of this container harder and harder and harder. They are colliding. Remember, molecules collide. Okay. These molecules are colliding against the sides of the container harder and harder and harder until what happens to the can? It explodes. Okay. So, the more heat, the higher the pressure. So equals higher pressure. Okay. Is the opposite true? The higher the pressure, the more heat. Okay? let's think about it in superhero terms. Superman. He takes a piece of graphite and he puts it in his hands and he presses as hard as he can, hard, and that graphite turns into a diamond and he gives it to Lois Lane. Okay. Yes, works the other way too. The higher the pressure, the hotter it is. Okay, we'll see some examples in class. I've got a little thing that you'll be able to hit and cause some heat with some pressure. It's pretty cool. And some other orbs that you can hit together also and show you that the higher the pressure, the more the heat. Okay, and that's it for today's lesson.